Welcome to the workshop. This week we are happy to welcome Lucas Janson, who's a professor at the Department of Statistics here at Harvard, and he's going to be presenting work on using knockoffs to find important variables with statistical guarantees. Thank you.
Thanks. Yeah, I'm really excited to be here and talk to you guys. One of the things I would very much like to do now, so I'm a brand new assistant professor at Harvard Stats. I just graduated with my PhD from Stanford, and this was my thesis work. It hasn't been that long, so this is what I'm still presenting. And I was teaching last semester, which took up all of my time. I am really excited to talk, especially to you guys, about this because something I really want to push more is getting people to use this stuff on their actual data. And you'll see, and I'll talk about this, that one of the things that I think is most exciting about this work is how much domain knowledge you can incorporate into it and use that to get out more statistical power and learn more about your data. And so I think it's sort of very ripe for good collaborations with people who have data and expertise on that data. So I'd love to hear from you guys about that. Also, happy Valentine's Day, everyone. I won't tell you how long it took me to put these little bumps on here and make the Harvard heart look like a, but I was pretty proud of that. So my goal today is to make you fall in love with knockoffs. All right, so let's start with the problem statement I'm trying to solve. So this is variable selection, controlled variable selection. So I have some outcome of interest, y. I'm going to call it a response or a dependent variable interchangeably. And then I have a whole bunch of potential explanatory variables or covariates or independent variables or features, x1 through xp. So p is the number of variables I'm looking through. And I want to select which of those p variables are actually important for determining the response. So I hope I don't have to sell you too hard on this. I imagine a lot of you think about problems like this, but there are applications for this in medicine, genetics, healthcare, where, for instance, your covariates may be genetic features or SNPs or mutations on the genome. And so you have a whole bunch of them, and you want to know which of them are related to, say, a disease or costs in the healthcare system. Or your covariates might come from electronic medical records. You know, how many visits have you had to the doctor? What have they prescribed you? What symptoms have you had? Things like that. Certainly in economics and political science, which as I understand accounts for a fair number of you, you have socioeconomic and demographic variables, and I imagine you're interested in how they might be related to future political opinion or income or factors like that. And then in industry and technology, it's now become very easy to collect a whole bunch of data on people's browsing behavior, internet history, and use that to try and understand which of those attributes of your internet behavior are going to determine whether you're going to click on an ad or engage with a website. And understanding that helps people build better marketing campaigns, build better products, and help their businesses. So here, these are just a few smatterings of people that use these things. So let me be very explicit, statistically precise, since this is, after all, an applied statistics workshop, about what I mean by controlled variable selection. So an important variable, I'm defining, I'll define an unimportant variable to be an xj that is conditionally independent of the response, given all the rest. So another way to say that is if I write down the conditional distribution of y, given all of the xj's together, then xj doesn't actually show up in it. That I can write that conditional distribution, the true conditional distribution of y given the rest, without actually using xj as an input. So that's what I'm calling an unimportant variable. And so anything that's not unimportant is important. So these are my unimportant variables. And I think this is a very natural definition of important variable because something called the Markov blanket of y is actually the composition of all these important variables under some very, very mild conditions. And the Markov blanket is exactly the smallest set S, such that if I give you the set of S, the set of x's in the set S, and ask you to predict y, you're going to have all the information you could possibly have about y that's contained in all of the x's. So if I give you all the x's and I tell you what S is, you know that you can throw away all the variables not in S without losing any information about y. And you know that if you throw away any variables in the set S, you've immediately lost your ability to understand y.
And it's keeping the variables whole, so you don't take like averages or principal components or anything.
No, when?
For S.
For S. S is just, I'm not sure what you mean.
It's the smallest set of variables.
Oh, of variables,
For
right.
each
So not
variable.
including linear combinations of variables or anything like that.
Right, just the
Yeah.
whole variable.
Whole variable, right. That's right. Yeah.
And a variable can, independent variable affect y, but it has such a small effect that it's still unimportant?
No. Well, not by this definition. So theoretically, no. But of course, this is a model, right? So when I call something an unimportant variable, in practice, of course, if something has such a small effect and it actually technically is important, I'm going to have no power to actually find it, right? But of course, it won't. But that's fine, right? Because I'm trying to, well, in a slide, I'll tell you exactly what I'm trying to control. But of course, not finding an unimportant variable or not finding an important variable will sort of be okay. Because if there was no effect essentially to find anyway, it's okay that we didn't find it. We wouldn't be able to find it with the data we have. Okay, so just to connect this to what I think is usually done in statistics, where we actually write down a model for y given x that looks like a linear model or a generalized linear model. And so then we have a whole bunch of coefficients, right? Because a linear model is just determined by its coefficients. And so actually the unimportant variables here, the ones that are conditionally independent of y, are exactly equivalent then to the zero coefficients in a generalized linear model. So this is a much more general definition of unimportant variable, right? Because there's actually no model underlying this, right? I haven't had to specify anything about what y given x looks like or what the distribution of x looks like. Here, if I do actually specify that y given x follows a generalized linear model, it's exactly equivalent to the usual variable selection problem, which is finding the non-zero coefficients in a linear model. Okay. Oh, okay, there we go. Okay, so, and then the control part of controlled variable selection, this is what I want to control. So I'm usually envisioning scenarios where P is fairly large. So I have lots of potential explanatory variables, which means that just doing individual inference on each variable is not going to be as useful as actually finding a set of important variables. And so what I want to control is the false discovery rate. There are other rates I could control using essentially the same procedure, but I'm going to focus on this one today. So this is just the expected fraction of false discoveries that I make. So I make some number of discoveries, some fraction of them are going to be false, and this is saying that in expectation, that fraction, I'm going to control it below some number q, like 10%. And in here, the convention here is that 0 over 0 equals 0. So if I don't make any discoveries, then I also haven't made any false discoveries, so I'm calling that a 0. But of course, I don't have any power, so that's still not great, but it's just a definition. So this is interpretable. It tends to be more powerful than controlling something like a family-wise error rate, which is a much more stringent condition. And so that's what we're going to aim for. Okay, so a sneak peek of what I'm going to tell you in the rest of this talk, this Model X knockoffs, which is the topic of this paper, and gosh, in all my Valentine's Day theme, I completely forgot to tell you about my collaborators, who are super important, and we're at the bottom of my title slide, so that I wouldn't forget to talk about them. But my collaborators are Emmanuel Candace at Stanford, and two collaborators at USC, Yingying Fan and Jinxi Liu, and they're great. I certainly don't want to forget to talk about them. Okay, let's get back to, where were we? Right, okay, so this paper with those wonderful collaborators is about Model X knockoffs, which is in some sense a particular instantiation of the knockoffs framework, and I'll talk about that in a second. And what it's going to do is use knowledge about X's distribution to solve the controlled variable selection problem that allows for any model for Y and X. It puts no restriction on the dimension, so it allows for there to be more or even many, many more variables than observations. It's completely non-asymptotic, so the control of the false discovery rate is going to be exact in finite samples, so there's no approximations here. It's exact under the conditions that we know something about X's distribution. And lastly, and I think very importantly, it's an extremely powerful procedure. So even though we have more stringent and rigorous guarantees than other procedures, we actually end up also being more powerful than those procedures because, well, we'll talk about why that is. So I will talk about all these things in the talk, but just to give a highlight and on the last point about practical performance, The application I'll focus on throughout this talk is to a genome-wide association study. And so this is where you have some outcome. So in this case, Crohn's disease, so just 0, 1. And your potential explanatory variables are single nucleotide polymorphisms, which are just locations on the genome where you check whether someone either has a mutation or they don't have a mutation. And so we had about 400,000 of those, about 500 subjects, about 40% of which are ones as opposed to zeros. And so we took this from a paper in 2007 that the authors kindly made their data available. And in that original paper, they aimed for a false discovery rate of about 10%, and they made 9 discoveries. And what they did is they used marginal tests. They made sort of a Bayesian argument to approximately control the false discovery rate at 10%. And when we did our same analysis, our own analysis, that is, we made twice as many discoveries. We have a much more rigorous guarantee on the false discovery rate. And we also were able to look at a later study that had many, many more samples, and so had much more power, and noticed that a lot of our new discoveries were actually confirmed in the later follow-up study.
So what's a discovery?
A discovery is a location on the genome, a mutation, that is an important variable for Crohn's disease.
In sample? In other words, do you know it's right? Like a discovery sounds like.
Do I know it's right? Okay, well,
or do you mean it's you found a strong association?
I found a strong conditional association,
Right.
and I mean that's certainly all I can say from the data, right? This is observational data exclusively. It would certainly be interesting to run a follow-up study, but as far as I know, people haven't. But that's all I can say here. So, but
What I mean is,
yeah, I'm not sure what you.
so if you did it the usual way, you'd have 5,000 subjects, 375,000 variables.
Mhm.
You'd run like some big correlation matrix. You'd circle the big ones, and you would declare that you found.
So that's
500.
importantly very different from what we're doing. So
Right.
that's
Why is that not a discovery? You know, how does this discovery different from that discovery?
well, okay. So it's different in a couple of ways. One, and just in its definition of what a discovery is, right? So I was very explicit about what I mean by discovery. And if you looked at correlations, you would not at all be answering that question, right? That would just be association. So just is Y and X related?
What I mean is what your definition is of discovery. I'm not disagreeing with you. I'm just
Yeah,
trying to
it's this.
understand what you mean.
This is my definition of a discovery
But
in a true underlying model.
I know, but you can't ever observe that. So
Right.
so
Oh,
what-
I guess this is my. Sorry, you're right. This is my definition of a true non-null. I apologize. What I'm calling a discovery is anything in this set S hat, and this is the guarantee I'm making about that set of S hats, that the
So you
expected
have-
fraction of false discoveries among the S hats.
So you have 9. You have 18 claims of discovery.
Exactly. Yes.
And some of and you believe, based upon your abstract model, that of course is a model that
There is no model here, but it's completely model-free in that
your
sense.
abstract. Well, that's a model.
This
Well,
is not a model.
Well, it's a theoretical claim, a theoretical condition,
Yeah, it's a theoretical.
which you can't
yeah.
test in your data.
This isn't a condition. This isn't an assumption, right? This is a property of a distribution. All distributions have properties, right? This is a property that is either true or false in any distribution. So this definition of like there are non-null variables and there are null
What I mean
variables.
is, for your 18 discoveries,
Yeah.
Can any of them? I mean, according to your analysis,
Mhm.
10% of them might be wrong, and 90%
Probably,
might be
yeah.
right.
Mhm.
And how do we know whether this turned out to be accurate in these data? I mean, we might do cross-validation or out-of-sample prediction or something like that.
Cross-validation wouldn't really tell us much of anything about this because that's really only a predictive algorithm, right? It could tell us whether those variables are good at predicting Y, but they can't tell us anything about whether they're actually conditionally independent of Y. And so what we'd have to do, well, we would have to do a follow-up study where people actually study and that's usually how genome-wide association studies work, is that because there's a huge set of variables to select from, if you find a set of 20, that means, okay, now I take maybe 20 postdocs and set them each to actually understand these variables.
Okay, let me propose a test to get at what Gary's
Please.
saying. So let's
Okay.
say you divide your 5,000 samples in half,
Mhm.
and you run your procedure on the first half and the second half, and you're going to get some number of discoveries in each of them. What do we think those discoveries are? How are they going to compare? Are they going to be the same set of precisely 18? Is there going to be some non-overlap? And then what do we
Probably some non-overlap.
What do we learn from that like kind of disconnect? between
Actually,
those
you'll
two
get
sets?
many fewer. You won't get 18 because your n's smaller.
Surely, yes.
Right. Because
As
of
with
the
any
ratio.
procedure, yeah. You'll have less power with less samples. So yeah, they won't exactly overlap, just like any procedure. I mean, you wouldn't. If they overlap, that'd be weird, right? Or sorry, if they were exactly the same, that would be weird. They should definitely overlap, but they won't be exactly the same. And I don't know. That's and their discoveries, right? So they satisfy this property, just like any. I guess I don't know how this is different from other hypothesis testing in the sense that like if I had a drug that I was testing and just a single thing, and I just want to know if it's important or not, if I split my sample in half, I might get the same answer in my both halves of my samples.
But so say
I don't know
on,
what it'll tell me.
SNP number 10, I find its discovery in the first half of my sample,
Uh-huh.
but in the second half I find it is not a discovery.
Yeah.
What do I learn from that? Do I say it's a discovery? Do I say it's not a discovery? How do I resolve this? Is that at all getting at what your question
Yeah,
was?
I just think that like at least in the literatures that we read, gosh, you can't call that a discovery because you don't mean that that's the truth.
Of course not. No, this is a.
It's like
I don't. But I can never know the truth, right? There's randomness in my data, so all I can do is say, okay, I've found a set of variables, and I think most of them are true in the sense that I've defined here, and that's all I can say. I can't say that all of them are true.
But how do you make your what we're asking you about is how do you make yourself vulnerable to being proven wrong? So you have a theory here, and you have a disciplined way of thinking about things,
Mhm.
and this produces 18 claimed truths,
Mm-hmm.
and so now suppose you were wrong, how would we know?
We would. 1 second.
Can I answer Gary's question?
Sure. Go ahead. I will get back and answer your question. Yeah.
Do you think we can, like with the 5,000 sample you have, can we do a holdout training? Like to use what you did on the training and then just test on the holdout? Would that feel satisfactory? Like,
That's one way we do.
So, but that's just sample splitting, right? So that I don't think that tells you anything in almost any statistical problem, right? So like if I'm so like simplest statistical problem is like, does this drug work or not, right? I have a randomized trial. I actually assign half the people to the drug or not, and if I take half my sample and I get a significant result on the first half, and then I take the second half of my sample and I get an insignificant result on that sample, that doesn't necessarily tell me anything, right?
we test on the holdout.
It tells you a lot if you're.
Depends on your power, right?
No, it tells you a ton. Because what we're afraid of is
Yeah.
you're using the first sample
Yeah.
to data mine.
Oh, but there's okay,
Right, to just, find things that seem.
but there's no
consistent
data
with-
mining here.
That seem, no, I understand, but that seem consistent with your hypothesis, whatever it is. And then you use the out of sample training set or second set for
Right.
Aaron to make yourself vulnerable to being proven wrong.
Okay,
And then we get to see whether it's wrong or not.
I see. So your concern is that there's some sort of overfitting.
But
That goes
that's-
on.
That's one thing that can go wrong, yeah.
Okay, but I guess, I mean, this guarantee. So if I did some sort of overfitting, right, that would invalidate any guarantees I made, right? Like just like if I had a, well, I don't know how it would overfit to a single drug, which either works or not. But
So when you say guaranteed, do you mean
Yeah.
that if we repeated this entire study,
Yeah.
got 5,000 more observations
Yeah.
from 375,000 variables, and we did this again,
Yeah.
and we followed your procedure,
Yeah.
we would find the same 18 discoveries.
oh, of course not. I mean, that's just like if I did a simple hypothesis test, I wouldn't expect to get the exact same result if I did it again on
Okay,
different data.
So
right?
so that's what I mean. So what's our claim about the future, or about a different data set, or about the nature of Crohn's disease?
Okay, so maybe I can frame it this way. So if I take the 18 things that I discover and then collect a new data set which has infinitely many samples, right? So that I would actually have 100% power, right? Then on average, over many different 5,000 sample things, right? Because I can only say things on average, 90% of those things I discover will actually be found in the 100% power infinite sample setting. Which is telling me the ground truth, right? If I have infinitely many samples, I have the entire population and I just know the truth, right?
Okay. And this will, and your point is, that will always work.
That
And
will
you don't
always
need,
work.
you
Yes.
wouldn't be more confident if you did draw the infinite samples and found.
Well,
and
surely if I had
followed-
infinite samples, I would be more confident. But
Well, if you followed your procedure,
Yeah.
you are basically 100% certain that if you followed your procedure with these infinite samples, you would find 90% of them would be accurate.
Yeah, of course there will be some conditions, right? I need to know some information about my data in order to run my procedure. But yes, there's no concern of overfitting, which seems to be your main concern, where you have a holdout set and an in-sample set. There is, I'll be very explicit about what you're allowed to look at and what you're not allowed to look at, such that these guarantees hold exactly. This is not approximate. This is not dependent on you. Well, I guess I have a procedure, and if you follow that procedure, then yes, this is a mathematical guarantee.
I think Gary's question is, to what extent do you rely on some modeling assumptions in discovering these important variables?
Oh, okay. If that was your question, then I'm going to get to the modeling assumptions later. But is that actually your question? I mean,
Well, why don't we see?
yeah, we'll see.
I'm just thinking about what you claim to be an advantage here, and is it
What have I
advantageous
claimed to
that
be?
we have more non-unimportant variables that are now statistically significant? Well, you ask what is an important variable, but you're defining it by its contrapositive, right? You're saying we consider it to be you're defining what is unimportant. So I'm assuming that what you're saying is important is that which is not unimportant,
Correct?
right?
Yeah.
It's just okay.
Yeah.
All right. That's.
I mean, I think that's just
do
because
you-
it's the easiest formally way to do it. I could just define
Yeah,
my
yeah.
important variables to be conditionally dependent on
sure,
y given
sure,
the rest.
but it's
Just put a line through this, and then that would define the important variables. But
right, but it's like the same concept as discovery, right? Are we discovering important findings? Well, and is it advantageous, as you say, to have more of these important discoveries?
I think so. Yes, I think we want to
Okay.
discover as much as possible, right? If there are more important things to discover, then yes.
Not if they're not true. I mean,
Well, right. So that's why I'm guaranteeing that the fraction I discover that are not true stays below q
But
in expectation.
You're presumably going to make some assumptions now.
Yeah, of course.
Okay, so then.
I haven't gotten there yet. Yeah.
So I think sometimes the assumptions will be wrong.
Surely.
Mhm.
Yeah.
And so then I want to know that you're vulnerable to that being revealed.
Okay. So you
rather
want to know
than-
about robustness.
No,
Robustness
I
to
wanna know
my
what-
assumptions only being approximately correct, right?
Yeah,
Okay. So that's something I'm going to address
I
later.
mean, it's like saying every time I have a p-value below 0.5, I'm going to call that a discovery. Actually,
Okay.
that seems unfair.
Well, it depends how you got your p-value.
It seems utterly unfair. Because no matter what, there's going to be some assumption there.
Yeah, that's true.
All right, let go. Yeah, let's see what it is.
I have another naive question before we proceed. Because
Sure. We have an hour and a half. I can answer questions all day.
I'm just wondering if, so by your definition, a variable is important if and only if it's in the Markov blanket. Is that true or not?
That is almost true because the Markov blanket technically is not exactly the same as this. You can have weird things that if you have two variables that are exactly the same, like they're stochastically identical, so every time I collect a new variable xj plus 1 equals xj, then the Markov blanket isn't well defined because you can include one or the other like this. There's an identifiability problem. So essentially, assuming that there is an identifiable set here, and right, if you have exactly identical two variables that are exactly identical, then you should throw one of them away, right? You can't possibly answer this question at all in your data, right? Even with infinite data, right, you wouldn't be able to answer this question. So, but modulo that very minor technical issue, then yes, that is exactly what I'm saying. Okay, I'm going to move on now. And hopefully address a lot of these things, because these are, when we talk about robustness and assumptions, that's like the first thing I'm going to try and address, even before I tell you what my procedure is, actually. Okay, but first I want to tell you a little bit what's out there, just to give you some context for what I've done. So the controlled variable selection problem in the sort of simplest setting assumes a Gaussian linear model, homoscedastic Gaussian linear model that's low dimensional. So you have more observations than potential explanatory variables. And in this setting, we actually sort of know how to solve this. So ordinary least squares theory gives exact p-values, again, under this model, but conditioning on x for testing whether each beta j is 0, which again is equivalent to my hypothesis, my null variables under this linear model. And then we can plug those p-values into the Benjamini-Hochberg procedure, which is a procedure that takes in a bunch of p-values, spits out a selected set, and that also has false discovery rate guarantees. Now, There's a slight caveat that actually the false discovery rate guarantees of the Benjamin-Hodgberg procedures assume independent p-values, which will not be the case here. There is a more conservative procedure that doesn't assume independence and which would actually give you exact control guarantees, but it's quite conservative, and in practice, the Benjamin-Hodgberg procedure is actually extremely robust. It's just an empirical finding that I wish we understood better theoretically, but nevertheless, I would consider that in practice, Benjamin-Hodgberg applied to OLS p-values is going to pretty much solve this procedure if you can actually feel good about having a low-dimensional linear model. And also, and then in terms of power, if your n and your p are sort of close, you are not going to be very powerful because ordinary least squares, it's not a very good procedure when n and p are close because you end up with almost rank deficiency and really high variance estimates of your coefficients. Okay, so when we make things a little bit harder and move to generalized linear models, we already have an extra challenge, which is that our p-values become asymptotic. So we don't have ordinary least squares theory, which gives us exact t statistics. We only have asymptotic p-values that assume n goes to infinity while p stays fixed. And unfortunately, those can be really far from valid in practice. So this is something I want to emphasize that I think it wasn't something that I understood super well before I started this project. But that this is just taking, in R, you use GLM and it spits out some p-values. And here I have n is definitely bigger than p. It's more than double p. And these are all null p-values, and this is a histogram. So these should be uniform, right, if these were valid. These are really far from uniform, right? These are hugely overweighted near 0. This is exactly what you don't want, right? If you use these p-values and think that they're p-values, you either plug them into something like the Benjamin-Hodgberg procedure or you use them marginally, just each one of them individually, you are going to get nowhere close to correct statistical guarantees, and that's because these p-values are only valid asymptotically as n goes to infinity and p stays fixed, which is not a good approximation when n and p are even remotely comparable. If your n is 20 or 100 times p, probably you're fine, but if it's 10 or less times p, you get things like this that, right, this is nowhere close to a valid p-value, right? So you're going to get completely invalid inference. Okay, so, come on. I am not good at clicking this once. Okay, here we go. So now, when we move to the even harder problem, as you might imagine, making things high dimensional is going to make things even worse. So this is something that there's actually been a fair amount of recent work on, is trying to get p-values in high dimensional generalized linear models, coming from the statistics community, the causal inference or econometrics communities, and there's this other statistics community about inference after selection. All of them are also asymptotic, so they're trying to get rid of some sort of bias that comes from using penalized estimation methods. And they're asymptotic, but they don't require n to go to infinity while p is fixed, of course, because they're high dimensional. But they still suffer from similar problems where in finite samples and in practice, they can be very far from valid. And they all require some sort of asymptotics, some sort of strong sparsity requirements, and some random design assumptions. So this is sort of what exists out there. These are all, as soon as you move away from the Gaussian homoscedastic low-dimensional linear model, we only have approximate methods, and in practice, those approximate methods can be pretty far from valid. So this is a sort of, there, okay, this is good enough. So this is just sort of a little summary about what are the important properties that you need to get valid inference in various regimes with existing procedures. So we have ordinary least squares plus the Benjamin-Hodgberg procedure essentially solves the low-dimensional linear model setting controlled variable selection problem. When we move outside of linear model to generalized linear models, but still in low dimensions, then we're still good under the asymptotic regime. But if we're not in that really big n compared to p setting, we can have big problems. And then similarly, when we move to high dimensions, we still need a generalized linear model. So we still need to assume a quite restrictive model on y given x. And we need some sort of asymptotic, some strong sparsity requirements, and some random design assumptions. But what I'm going to talk about today is a very different way of doing controlled variable selection, which actually doesn't involve p-values at all. And this is called the knockoffs procedure, the knockoffs framework. And the original paper was not written by me. This came out a few years ago. And it actually only applies in the low-dimensional Gaussian linear model setting again. So actually exactly the same as the first row, where in some sense we already had a solution, but it's a very different way of doing it. It can often be much more powerful because it does take advantage of sparsity, and it actually has, I said that there's that slight caveat in the ordinary least squares setting that the p-values aren't independent, so Benjamin-Hochberg doesn't exactly control the false discovery rate. Knockoffs does exactly control the false discovery rate. Okay, and then the subject of this talk will be the Model X knockoffs instantiation. And so, as I mentioned before, there will be no constraint on the dimension, no requirement for a model for y, so we're completely model-free with respect to y given x. You don't need to know anything about it, you don't need to assume anything about it. There's no asymptotics, and there's no sparsity requirement, since of course a sparsity would be a property of the model for y given x. But we are going to have, I put a little asterisk here to note that this is going to be a stronger random design assumption than here, because we're really shifting the burden of knowledge from y given x onto the model for x. Okay, so let's finally talk about the knockoffs idea. So that's just a little notation. I'm going to have little bold y as my actual data vector, right? So I talked about y and x before. Those were the random variables. Now y is actually an n by 1 column vector. xj is an n by 1 column vector, and I have p of those. And when I put them all together, I get the design matrix X, which is an n by p matrix. So in the original paper, there was a 3-step procedure. Well, there's always a 3-step procedure in knockoffs, but in the original paper, these are the details of those 3 steps. And you don't have to focus too much on this equation, except to notice that it's deterministic and it's geometric. But in this first step, what you do, and the idea behind knockoffs, is that you construct knockoffs of your original variable. So you have p original variables, and what we're going to do is we're construct knockoff variables, so fake, cheap versions of those x's that we can generate ourselves without going out and collecting new data, that are going to resemble x's in some important ways. And so this is the important ways in that the x tildes have to resemble the x's in the original knockoffs paper. We're going to have a different one for model x. And then we're going to use those knockoffs sort of as controls for the original variables. So we're going to say, okay, does y look like it's more related to xj, or does it look more like it's related to x tilde j? And because of the symmetries between xj and x tilde j, we'll actually be able to say statistically rigorous things about that comparison. Do I have a sort of a half question in the corner? Or
Well, I'm just looking at an assumption you're making. If that concerns you, we see that the original knockoff variables are pairwise exchangeable, taking any subset of variables and swapping them with their knockoffs.
Oh, you're way ahead of me.
Oh,
We haven't even gotten to my paper yet, which I think you're reading from. So, yeah, give me like 3 or 4 slides.
all right.
Then you can ask the same question.
Oh,
Okay.
it's out there.
Okay.
Submit it to.
So, okay. So the first step was to construct these knockoff variables, and I haven't told you exactly how to do that, but I'll get into that more when I talk about my procedure. In the second step, what we wanted to do is actually compute a measure of how related y seems to be to xj versus xj tilde. And so the knockoff statistic is going to be this scalar function that measures how much more related y seems to be to xj than it is to xj tilde. So we think that if y appears to be actually more related to the knockoff variable, which we constructed, so it's clearly fake, it's clearly not important, because it has nothing to do with the data, then that's not a very good sign for xj. Right?
So the knockoff variable it's not a function of the data, it's just like random numbers?
It's not a function of y. It's a function of x, but I'm not going to look, so that's important. So the x tilde will be constructed without looking at y.
But if it's a function of x, it should be important, because
Nope.
there's important variables in x, right?
Yes, but it's not important by my definition, which is that conditional on all the other variables, it has some effect on y, right? Every variable in x tilde must be conditionally independent of y given x. Because I didn't look at y, I only looked at x. So its relationship to y can only exist through x, but we're already accounting for x, and hence every single variable in x tilde is unimportant and null.
I'm just not sure. So are you allowed to set x tilde equal to x27?
You could, you wouldn't have any power, but
But if x27 is important, then x tilde is important, because it's the same variable.
technically you're breaking the procedure if you set it to be exactly equal, because then you have an identifiability problem again, because you have 2 identical variables. So this is the thing I talked about before, where there actually wouldn't be a well-defined.
So if I define it as a first principal component set, or that also
Same problem.
violates.
Yeah. So the first print. So okay, I can rephrase that. If you define x tilde 27 to be equal to x 27, then it is true that x tilde 27 is conditionally independent of y given x, right? Because we already have x27, right? So that is indeed, it will be null. If we set it to be the first principal component of x, the same is true, because we already have the first principal component of x from x.
Okay.
So it's giving us no new information, and that's exactly what I'm calling a null variable, is something that gives me no new information on top of all the other variables.
So how do they actually create the x tildes?
I'll get to that. Yeah. Okay, so this is computing the knockoff statistics, and there's a lot of vagueness here. I'm giving you an overview of the procedure. I'll go into more details later. But again, I'm going to focus on the actual procedure I'm presenting, which is the model X knockoffs. This is just the first instantiation of the knockoffs procedure. And again, this only works in the low-dimensional linear model.
And what's W?
W is my knockoff statistic, which again, I'm not telling you how I'm constructing it. You have a lot of flexibility in how you construct it, in fact, but again, I'll get into that more later. And then, okay, so you've constructed your knockoff variables. You've used those knockoff variables and your original variables to construct these WJs, and they're somehow measuring the relative importance. WJ measures the relative importance of xj versus x tilde j. And so a big positive WJ suggests that xj is more important, and small positive or especially negative WJs denote xj's that are probably not important, evidence against the rejecting xj. And so what we're going to do is we're going to take those PWJs and plug them into what is essentially a step-up procedure. And so we're first going to order the WJs by decreasing absolute value, and we're going to look at and then we're going to look at their signs. We're going to go down the list, and we're going to count the number of minuses we see. We're going to reject all the pluses we see, and we're going to count the number of minuses we see. We're going to keep track of the fraction of negatives over positives, and we're going to stop at the last time that this fraction is below q. And if it never goes below q, we make no rejections. And if we stop at the last time that this goes below q, we actually, and then reject all the positives that we've seen so far, that's going to give us the exact false discovery rate control guarantees under the assumption, in this case, that y follows a Gaussian linear model in x. Okay, so I had some comments, right? So you get exact finite sample FDR control. W can leverage sparsity, so W could be computed, for instance, as the lasso coefficient estimate in a y on x regression, and that's going to be more powerful because it actually uses the sparsity of the situation. But it requires a low-dimensional Gaussian linear model, and it relies heavily on the model for y, which, of course, in practice we often don't know a lot about. Okay, so one of the main issues with this procedure, okay, it has a linear model. I think probably you guys as applied statisticians wouldn't be super comfortable with that, but statisticians are often comfortable with linear models, which I think I take a little bit of issue with. But the thing that statisticians aren't comfortable with is assuming that we always have low-dimensional data, right? You can't pretend that n is approximately less than p. N and p are numbers, and if n is less than p, you can't even run the procedure I just told you about. So it's not just that it doesn't control the FDR, you literally can't even get an answer out. So extending this to high dimensions is a really important thing. And so to talk about generalizing this to high dimensions and to nonlinear models, we want to think about a generic idea of what the knockoffs framework is. So we still are going to have 3 steps, and in the first step, we're still going to think about constructing artificial versions of the variables. Now, it may not be in the same geometric deterministic way that we did in the last slide, but somehow we need to get these fake variables that act as controls for assessing the importance of the original variables. And then in the second step, we want to construct these knockoff statistics, which again, somehow, in a way that we will make precise soon, measure the relative importance of xj versus xj tilde. And then lastly, we're going to plug it into the exact same procedure as before. And what makes this work, and what's really fundamental to the knockoffs framework, is what's called the coin flipping property. I'm afraid to click again because it's going to do like a double click, but okay. The coin flipping property. So the key to knockoffs is that steps 1 and 2, so of course step 3 is staying fixed here. So I need to construct steps 1 and 2 such that the WJs have this really special coin flipping property, which is that conditional on the absolute values of the WJs, the signs of the null WJs are independently plus or minus 1 with probability half. So there's a couple things about this that make it, I mean, let's relate this to what we know, right? Like p-values, right? When we talk about p-values, something is a p-value if under the null it has a certain distribution, right? So this is saying something sort of similar, right? It's saying that, at least conditional on these absolute values, my null WJs have a specific distribution, which is just a coin flip, a plus or minus 1. I'm not saying anything about the non-nulls, and indeed I want them to be different distributions, otherwise I wouldn't be able to distinguish them. But so it's sort of like a p-value in that we have a specific known distribution under the null. But another thing that's important is that I'm actually turning this set of possibly very dependent x's into a set of independent WJs. So it's not just that I know their marginal null distributions, I actually know the full joint distribution of the null statistics. And that's really important. Okay, and it's important also that that this is true conditional on the absolute values of the WJs, because I use those to order the p-values. So of course, if the signs were really dependent on the magnitudes, and then I ordered things based on the magnitudes, I would have sort of biased what signs I'm seeing, and it wouldn't have the properties we want. So this is really the fundamental property that makes knockoffs tick. And so
Conditional of all the absolute values of WIs except WJ, right?
nope, a condition on all of them.
Oh.
Including WJ, right? So if I just had one W, what is this saying? If I just had one W, this is saying that W has a symmetric distribution if it's null, right? Because that means if I tell you the magnitude of W, I don't know anything about its sign. That's exactly what a symmetric random variable is, right? Okay. So finally, let's talk about model X knockoffs. And the key difference between model X knockoffs and the fixed X knockoffs that existed before is shifting that burden of knowledge from Y onto X. So when we talk about assumptions, we're going to talk about assumptions about the distribution for X as opposed to the distribution for Y given X. And so the thing that we get out of this, so by moving the assumptions over, we completely remove the requirement on low dimensionality. We remove, of course, the requirement on the conditional distribution of Y given X. Not only is it unconstrained, but we don't have to know anything about it. And something I didn't talk much about is we remove this sufficiency requirement on WJ, which we're going to see a little bit later. Gives us a lot of flexibility in what we use to measure variable importance, and it allows us to use some really cool things like really sophisticated and modern machine learning methods. And so we're really flexible. We can use a lot of, again, domain knowledge to make our procedure as powerful as possible. So the assumption I'm going to make, unquestionably a strong one, but it's a starting point, is that the rows of X are IID from some distribution, and that I know exactly what this distribution is. So I know it exactly, right? So this is a strong assumption. And to clarify, I'm saying the rows must be IID, not the columns. And actually, I'm going to put no, although we have to know G exactly, I'm not going to put any constraint on G. G can be anything. I just need to know it. And again, nothing about Y's distribution is assumed or needs to be known. And okay, and preliminary simulations, which I'm going to show you in the next slide. As I said, the first thing I'm going to address is robustness. Show that there seems to be some robustness to this strong assumption. Yeah.
Sorry, we still don't know how W was created from the X tildes, and we don't know how the X tildes were created.
Yep.
Okay.
That's because I think robustness is so important. Your first question, that I'm going to address robustness before I even tell you what my procedure is.
Okay.
But I promise I will tell you what my procedure is.
Okay.
Yeah, question.
So how do we overfit X distribution if we have to assume it? That's what
Well, so the point is that if I'm talking about robustness, right, that means that my assumptions don't hold. If my assumptions hold, I don't have to worry about robustness, right? If my assumptions hold, all my exact guarantees go through. I have exact false discovery rate control. I don't have to worry about anything.
No, you still
But-
have to, even if it's true, you still need to worry about it because you don't know whether it's true. And you got humans, which is really the real problem, who are adjusting G potentially to get, perhaps inadvertently, to get a result that they want. So robustness is important regardless.
I think this is a semantic difference, but if you know it's true, then if you have the true G, then presumably you know you have the true G, and if both of those hold, then you don't have to worry about robustness.
Oh, okay. Well,
So, but to your question,
no one else will believe that. So.
Well, fine, but the point was not really about that. The point was that you only have to worry about robustness because you or your reader or someone isn't sure that you know the exact G, right? So that's and if you aren't sure that you know the exact G, what do you have to do? You have to fit it to the X's you actually have, right? You have to take a guess at what g is, and probably how you're going to guess that g is you're going to try and learn it from the data that you have, right? Those are the x's you have. That's what you're going to try and do. So that means that you're actually fitting g to the distributions you have in your sample, which normally looks like overfitting, right? That's what happens if we were thinking about the usual setting where we have y and x and you overfit y given x's distribution, right? For instance, you do variable selection and then pretend that you started out with those variables in the first place and then do ordinary least squares, right? That would be first you fit your model to the data and then you pretend you knew that model all along and proceed. That's sort of what you'd be doing here. You fit your x distribution to the data, then pretend you knew that that was the true distribution and proceed. That's the overfitting I'm talking about.
Which is what sort of anyone would do in practice.
Yep, exactly.
Okay.
So that's what I'm trying to address.
That thing that actually we don't have to assume we know G, because in fact, if we just fit G from our data, that will actually do good enough.
Well, what I'm going to try and convince you is that I have robustness. The exact theoretical guarantees won't hold. My theorems won't go through. But that in practice, we seem to see that, yes, that we still get the false discovery rate control that we want. When we simulate things and actually, so that we know the ground truth, and then we do what people would actually do in practice, we find that this thing seems to work. That's what robustness means to me.
So I think Gary's worry was people will try to fit G from X in a way to basically get the things they want at the end. I think that's the worry of how do you deal with that problem.
Right, so that's overfitting, right?
Yeah.
So that's what I'm going to try and convince you is not as much of a problem as it might be. Okay, that's what this slide is. So, what I'm showing you on this slide is a little complicated, but the x-axis you can just think of as the error in my estimate. And it's actually a particular, I'm not measuring it in terms of overfitting error, but what I'm actually doing in this simulation is I'm generating, this is high dimensional data, so p is about twice n. I'm generating this data from, of course, a known model because it's a simulation so that I can actually measure the ground truth and actually know what the power and false discovery rate is exactly by repeating it many times. And what I'm going to do is I'm going to take the x's I actually have in the simulation I just generated. So I have my 800 by 1500 dimensional x, and I'm going to fit some model to it and then pretend that that's the true model and run my procedure. So that's what someone would do in practice, right?
So what's the quantity that you're trying to estimate that you're measuring on the horizontal axis with?
The error of?
Yeah, the error
the covariance matrix.
The covariance matrix of what?
Of x, right? So this is a AR1, so this is it's a Gaussian with Toeplitz covariance matrix, and I'm going to use different estimates of that covariance matrix, plug it in, so I have the wrong distribution, right? Because I've estimated my covariance in sample.
Sorry, I'm not, I mean, the rows of x are independent. So
Yep.
I don't know why do you have AR1?
It's the columns. The columns have that distribution. The columns are, you can think of them as a time series that's AR1, or more generally, right? You just think of them as a joint distribution which is multivariate Gaussian with Toeplitz 0.3 covariance matrix.
Okay, so you're trying to estimate that 0.3? Like
No.
that's-
Because I'm not telling my procedure, I'm not telling my procedure that it's AR1.
You're trying to estimate the uncertainty in the 0.3
No, I'm trying to estimate the entire covariance matrix
of.
because I don't know the covariance matrix.
The columns.
Yeah, I can write down what the
But not
covariance
the
matrix is.
Sorry, it's just terminology again.
Uh-huh.
The covariance of the columns is observed. So
The true covariance. They
well, we
come from a
have
true
all the numbers
distribution,
in
right?
the columns, so you
Remember
can-
there was G, this thing that I assumed I knew, which was the distribution of the x. This is my matrix, n by p. So I'm saying that in this simulation, it equals normal 0 p by 1, or is the rows are IID, normal 0 p by 1, sigma p by p, where sigma is 1 row squared, row cubed, inverse, I think. No, not inverse. Right, this is the covariance matrix of an AR1.
I got it.
Right, so this is my covariance matrix, and what I'm going to do is, since I don't know this covariance matrix, I'm going to estimate it using my x's. So we have a high-dimensional covariance matrix estimation problem. That's a hard problem. And so what we're going to see in a second is that, my first point on this plot, so on the x-axis we have the relative Frobenius norm error, which is essentially saying what is the relative error in my estimate of the covariance matrix that I fit in sample on average. So at 1, that says I basically have 100% error.
And it's some kind of scalar difference between.
Yeah, I can just write it. That's So this is the Frobenius norm, which is just the sum of the squared entries of the matrix, right? Okay. Okay, so we start on the left-hand side, and we have, so if I knew the exact covariance, and that's what I plugged in for my sigma hat, of course I would have 0 Frobenius norm error, and I would have about 75% power, and I would get exact false discovery rate control, because that's a theorem, so I know that that's true, right? So this is where I start, and the question is, what happens when I start using estimators that are estimated, again, in sample, so overfit to the data I actually have? Okay, so the first thing I might try is a graphical lasso. It just so happens that this covariance matrix has an inverse covariance matrix that's sparse, so the graphical lasso is probably a pretty good thing to do. If you don't know what the graphical lasso is, it doesn't matter. All that matters is that it has low-ish error. I mean, this is a hard problem, so we're already at 50% relative error. So in absolute terms, this is a pretty bad estimator, right? We're off by 50%. And yet our power really hasn't changed, and our false discovery rate really hasn't changed. Now, I can keep making this estimator worse and worse by just trying other estimators that are sort of dumber. And so what I'm going to do is just take convex combinations of the empirical covariance matrix, which we know is a really bad estimate, right? Because we're in a high-dimensional setting, so the empirical covariance matrix is rank deficient. It's going to be really terrible. And so we're taking mixtures of that with the true covariance matrix. So the more weight I put on the empirical covariance, the worse it's going to get.
Sorry.
Yeah.
It seems to me that what you were trying to demonstrate was that if G changes, then your discoveries remain the same, or roughly the same, or something like that.
Why should the discoveries remain, or the
because
amount of
that's-
errors
that-
I'm making remains the same, right? That's the only,
But
I'm
the
not,
proce-
that's my guarantee, right?
Well, I'm losing track of the big picture, right? So the goal of the whole procedure was those 18 discoveries, right?
It was discoveries, yeah?
Yeah, just right. And so I don't quite see, shouldn't it be robustness to that kind of results? Like what? Like is the goal to estimate sigma?
No. The goal is to get those discoveries. So everything I'm plotting here, right, has nothing to do with sigma. Sigma is just an intermediary that I need to plug in a sigma in order to run my procedure. So I'm showing that if I have a bad estimate of sigma, I still get all the properties that I want out of those 18 discoveries, which is that I get high power, so there's a lot of them, that's what I want, and I make a fraction of false discoveries that's below 10%.
Oh, and that's your version of just the wrong distribution.
Yeah, is G being wrong, and it is wrong, right? So if I plug in sigma hat instead of sigma, I'm using the wrong distribution.
I see. So you're
Right.
keeping G the same and you're changing sigma.
Exactly, right. So as I move right, I'm plugging in worse and worse estimates of G.
Okay, and so then what's the process by which you're choosing the wrong estimates of sigma?
So here I'm estimating by the graphical lasso based on the samples I have. And then the next one, I'm using a 50% combination of the empirical covariance matrix and the true covariance matrix.
So they're all in some kind of sense consistent. But
No,
you
graphical lasso is not consistent in
well,
high
they
dimensions.
must have, I don't mean consistent, I mean, they have properties that whoever came up with the graphical lasso like. Right?
Okay, sure.
You know?
But those properties don't hold here, so it's like.
Right.
So what matters, I think, is the relative, what's on the x-axis here, right? So it doesn't matter what properties they have, it matters how well they actually do in this problem, right?
Okay.
And what I'm telling you on the x-axis is exactly how well they do on this problem.
Okay.
And so I'm going to make them do worse, and I'm just taking worse and worse estimators. I'm going to make them do worse, and I'm going to see what happens to the things I care about, which are power and statistical guarantees,
And how do
the
you
false
calculate
discovery
the
rate.
false discovery rate, which is the thing you actually care about.
Well, I know the true distribution, so I know exactly which are the important and unimportant variables, and I can just measure that each time I run it and do it many times. So these are all averages over 1,000 replications. Okay, so I'm going to keep moving to the right now. So I'm getting worse and worse estimators as I put more and more weight on the empirical covariance matrix. And I think something sort of interesting happens. So let me stop here, because I usually like stopping here, because this is where we reach about 100% relative error. So this is, again, in absolute terms, a really, really bad estimate of the true distribution G. And yet we've only lost about 10, 12% power, and our false discovery rate is still under control. Now if I keep going and move to the 100% empirical covariance matrix, actually what I end up doing is forcing my knockoffs. If I think that my true covariance matrix is equal to this rank deficient covariance matrix, which actually is saying that I'm breaking this assumption that my variables are not redundant, because if I have a rank deficient covariance matrix, I actually have redundant variables, or I think I have redundant variables. what I'm actually forced to do is create knockoff variables that are actually identical to x. So I just am forced to use x tilde equals x, which means I'm never going to be able to distinguish between x and x tilde, and my wj's are all going to be 0 because they look exactly the same, so they're exactly equally related to y, and I'm going to have no power and no false discovery rate. I'm just going to make no discoveries, right? So this is, of course, on the right-hand side of this plot. That's not a great setting, but there's a few things about this plot that I find appealing. First, I see some hands almost going up. Yeah, go ahead.
So how, as a researcher, could you do any of these 50% empirical things? This is more
Nope.
for
No.
right, because you couldn't actually do that, right?
No.
So what would you?
Well, you could do the graphical SO.
Right. So what would you do as a researcher besides something like the graph lasso in this case?
Just any. I mean, there's an entire field on covariance matrix estimation, all of which are talking about estimators that estimate things. This was just a choice, right? I could have picked other estimators that fit on this graph. I tried to pick bad ones so that I could move to the right, right? If I used really, really good ones, then this graph would be stuck on the left-hand side and it wouldn't be showing as much robustness, right?
So when you pick worse estimators of the covariance matrix,
Mhm.
and therefore you're violating the assumption more, which
Yep.
is really the only reason you're doing this,
Exactly.
you do better
Better.
because the false discovery rate drops.
I think we're looking at different graphs. No. Well, the false discovery rate drops to 0, but so does the power, so that's not a useful procedure. I can definitely always control the false discovery rate if you don't need any power. But I think it is interesting. It is. I'm not going to say it's better as you move to the right here, but it's more conservative as you move to the right. And I think that's actually in very stark contrast to what normally happens when you overfit. Because when you have a procedure that makes assumptions about y given x, and you overfit the distribution of y given x, what happens if you did the exact same thing where on the x-axis here I was looking at overfitting error in y given x, I would see this go up, right? And I would see my power go up, right? It would be essentially the inverse of this graph. And the fundamental difference here is that when we make assumptions about x, and then we're wrong about those assumptions in x, the thing is that we're not, the questions we're answering here are not questions about x. The questions we're answering here are questions about y given x. And so it actually makes a difference whether you're overfitting the distribution of y given x while answering questions about y given x versus when you're overfitting x while answering questions about y given x. And I think the difference is, and this is something we'd like to understand theoretically better, but I think intuitively it makes some sense that the overfitting we're doing, no matter how much we overfit, it's not easy for us to cheat because the thing we're overfitting is not the object we're actually trying to answer a question about. And that's very different from the case when you're modeling y given x, and then your overfitting is actually pretending you know more about the truth than you do. Whereas here, it's pretending you know more about the truth that you're trying to find than you do. Whereas here, we're pretending we know more about the truth, but that truth is essentially orthogonal to the questions that we're answering. And so it doesn't seem to hurt our inference. Yeah.
It is a little weird though that I don't have a precisely defined concept of this in my mind, but like you could also think about something like the true discovery rate or something about.
That's what the power is, right? The true discovery rate? The rate at which I find I make true discoveries. So this is what fraction of the true discoveries I find. So a 1.0 means I find all the true non-nulls, and this is what fraction of the false discoveries I make. So these two together are the type 1 and type 2 error, or 1 minus them. Yeah.
That makes sense.
Okay, so this is my preliminary simulation on robustness. I don't have time to show you much more about that because I have to tell you about what the procedure is and explain why it should work. But I claim that there seems to be some empirical evidence that this thing is robust. Okay, so I told you about shifting this burden of knowledge, and I think that's a really important point about this. Wow, is it already 1:10? Whew. All right, we're gonna go super fast. Who cares when it's appropriate? I claim it's appropriate in genome-wide association studies because we have IAD rows. We have a ton of knowledge about the structure of X, actually. Biologists have studied what SNPs look like along the genome. They have very good hidden Markov models, and they've used these for imputation because they had very bad data collection procedures, so they needed to impute missing values. And so we can actually take advantage of a lot of domain knowledge that is about the distribution of X, and yet they still have no idea, right, what the conditional distribution of getting diabetes given your genome looks like, right? That's something they have no idea about the structure of, whereas we actually have a lot of information about the structure of the X distribution. And we have a whole lot of unsupervised data, which if we have a whole bunch of unsupervised X's, so X's with no corresponding Y, we can use all of those together to improve our estimate of the distribution of X. And that's not true if we want to make assumptions about Y given X, right? Because unsupervised data doesn't tell us anything about the distribution of Y given X. But we only need to know about the distribution of X. So unsupervised data, which certainly exists in genomics, because you have lots of studies that measure different responses, can be used. Okay, so finally, let me tell you what the actual Model X knockoffs procedure is. On slide 12 and starting on hour 2. So the first step, we are going to construct knockoffs that obey this pairwise exchangeability property. So instead of that geometric deterministic property that we saw in the fixed X knockoffs, we want to construct knockoffs that obey this. So if I take my augmented matrix that has X and X tilde next to it, so it's a n by 2p matrix, and then I take that matrix and I swap the jth and the j plus pth column, so I'm swapping a variable with its knockoff, then the full joint 2p by n dimensional distribution doesn't change. That's what I want out of my knockoffs. In step 2, I want to construct, I have essentially a straightforward procedure for constructing the WJs in a flexible way. So I want these Z's, yeah.
Sorry, in the middle, XP, X tilde 1, is there a comma or something?
Well, there's a space between them, yeah. Yeah. That's, yeah, space concatenation. Okay, so here I want to construct variable importance measure Z, which can be constructed almost however you want. So you have a lot of flexibility in how you construct these. This is another place where you can input a lot of domain knowledge about what you think Y given X might look like. So the nice thing is that you don't need to know what Y given X looks like, but if you have a good guess as to what it looks like, you can use that knowledge and it'll improve your power. If you're wrong, you'll just lose power. You won't lose false discovery rate control because we make no assumptions about Y given X. But you can be much more powerful if you really know what you're looking for. And that's where you would input into your variable importance measure Z. So if you think it followed a linear model, your Z should look like the coefficient from a linear model. If you think it follows a quadratic model, same thing. So what you're going to do, you take these Z's, so I'm going to have one for each knockoff and each original variable. I have 2p of them. I'm going to plug them into this anti-symmetric function, so just a function whose two arguments, if you swap them, you get a negative sign out in front. So for instance, Z1 minus Z2, right? If I swap the two arguments, I get the same thing with a minus sign in front. And my WJ is just going to be Fj of the jth variable importance measure and the jth knockoff variable importance measure. And then step 3 is the same as before. I'm going to plug those WJs into that. Now I'm going to tell you a little more about the step 1 and 2, which are really the hard part. So first, we proved that you can construct valid and non-trivial knockoffs, so knockoffs with power, for any given X distribution. So this is a completely general algorithm that constructs valid knockoff variables. It may be computationally very hard to run, but theoretically at least it says that in principle, no matter what X's distribution is, as long as you know it, you can run this algorithm and construct valid knockoffs and have some power. So this tells us something about the generality of our method. That said, again, there could be computational challenges in actually running this. It requires these conditional distributions. L is like the law. These conditional distributions, we need to be able to sample from them. We know that that's often hard if we have complicated distributions. So we thought about the simplest setting where we have X being multivariate Gaussian and whether we could do something more clever or faster. And so what we came up with is that if you have multivariate Gaussian X's, then our condition, our exchangeability condition, is exactly this. It's on the covariance matrix of all the 2p things together. And what it says is that it looks in the top corner, of course, we have the covariance of X. Here, we again have the covariance of X. And then on the off-diagonal blocks, we have the covariance of X minus a diagonal vector. So S is a vector that I haven't told you how to get yet. But what we can do is something like, we want S to be big, right? Because S is, or the diagonal of sigma minus S is the correlation between X and X tilde. So we want that to be as small as possible, so we want S to be as big as possible, so that X and X tilde are as different as possible, because that's what allows us to have power. We want to be able to distinguish them, because if they're the same, we won't be able to tell them apart, and we won't be able to say that the original variable looks more important than the knockoff variable. So we want to make S as big as possible, so we can do linear algebra or semi-definite programming to say something like, okay, maximize the sum of the absolute values of S, subject to the fact that this is a positive semi-definite matrix, which means it's a valid covariance matrix. And so I can just plug it in. That's actually a convex problem. I can solve that and get a bunch of S's that way. There are some other ways to do that. I'm not going to go into details. And more recently, actually, people have come up with very computationally fast constructions if your X follows a Markov chain or follows a hidden Markov model, which is especially relevant because hidden Markov models are actually what biologists use to model SNPs along the genome. So we now have an exact construction for hidden Markov models that's extremely computationally fast. Jeez. Trigger happy button. Okay, here we go. So now step 2, constructing knockoff statistics. Remember, these are just an anti-symmetric function of variable importance measures. And something you might just have in the back of your head is an example, although again, there's a lot of options for this. Z could be the magnitude of the fitted coefficient beta from a lasso regression of Y on the augmented design matrix. So I'm going to get 2 P coefficient estimates from this. I'm going to take their absolute values. That'll be my ZJ. And then I'm going to plug them into the simplest anti-symmetric function, which is just the difference of the two things. And what I'm going to get is a lasso coefficient difference statistic, which just takes my estimate of the jth coefficient, absolute value, minus the estimate of my jth knockoff coefficient in absolute value. Okay, so this is just something to ground what I'm talking about. And then the question is, how do we get this coin flipping property? So this slide is about the coin flipping property and how you get it and why it's why it works. So this is the assumption we make, which is that our x's satisfy this. And I told you a little bit how we can accomplish that. Now, the coin flipping property for Wj means that for unimportant j, if I look at, I'm about to prove the coin flipping property. So if I look at the joint distribution of Zj and Zj tilde, so this is just a two-dimensional distribution, I can write these Zijs, they're just functions of y and the x's and x tildes, right? So I've just expanded this into functional form. I haven't done anything yet. But I'm focusing on xj and xj tilde. All the rest I'm just leaving as dots. So what I have up here tells me that when I swap xj and xj tilde, I haven't changed the joint distribution of the x's. And since it's null and they're conditionally independent of y, that means that I actually haven't changed the full joint distribution of the y's and the x's, which means that the inputs to these two functions are actually identically distributed to the inputs to the two functions in the line above, which means that the distribution of these two variables are the same. Okay, so I've got an equality in distribution here. Now the slightly trickier part is to note that what Zj tilde does is it measures so up here, right? It's measuring the variable importance of the values that actually fall in this column, right? That's what it's doing. It doesn't know that these are random variables, it's just a function, right? So it's spitting out some values that depend on how related y is to the variables in this column given all the other columns. And so what happens when I actually swap these inputs is now Zj tilde is measuring the importance of the values in this column given all the rest, which is exactly what this is doing, right? Because now the values in this column are xj, and this is measuring the values in this column, which is also xj, which means that if I swap these back and swap the tildes on the z's, I get exact equality. This is the trick that makes it work, is that I can now swap the tildes on my z's, swap these x's back, and I actually get the exact same thing. And so now if I reduce the functional notation, what I've shown is that Zj tilde is equal in distribution to Zj tilde Zj for the null variables j. And now if I use my anti-symmetric function, so I've just shown this, that I get equality in distribution when I swap the inputs, and then when I swap them back I get a minus sign because of anti-symmetry, and I've just shown that W is symmetric, which again is the one-dimensional version of this coin flipping property, and it's very easy to generalize this proof to many dimensions to show that actually if you swap any of these you get equality in distribution, and that's exactly what IID coin flips looks like. So this is at least theoretically I think the most important slide because it tells you really what makes knockoffs work. The next slide I think is really exciting from an applied and power perspective because it tells us that there's a lot of things we can do to incorporate prior information and be flexible to what the conditional distribution of y given x is. And that's the thing we're trying to learn about, right? We're trying to discover the important variables in the true distribution. So first of all, we can use cross-validation to choose the penalty parameter in the lasso coefficient difference. That was something already actually that we couldn't do in the fixed x design because of that sufficiency property I briefly alluded to. But at a much higher level, we can be adaptive to a lot of things. So for instance, we could use cross-validation to choose between totally different procedures. So for instance, if I have no idea what y given x looks like, maybe it's really, really rough or maybe it's really smooth, I could try fitting a random forest, which I think would work well if I have a really, really rough y given x function, because it's totally non-parametric, it allows for discontinuities. And then I could also try fitting a lasso, which if things are really, really smooth, right, I'm fitting a really flat surface to it, that might work well in the smooth case. I don't know which one is going to work better. I can fit both, look at the cross-validated error, pick the one that has lower cross-validated error, so it seems to work better, and then derive a variable importance measure from that, and I'm going to get exact false discovery rate control. This is completely valid. Knockoff statistic. And I think that's one of the things that's exciting about this is that the concerns you might have about overfitting, where you look at your data and you make decisions about how you do your procedure, those are actually acceptable in this framework. And all the guarantees I have still go through, even if you do this overfitting. And in fact, the analyst can look at the entire data set as long as you don't tell the analyst which of the x and x tilde are which. So it can actually, the analyst can choose how they want to select z by looking at the entire vector y. So you get to see y completely. You get to see all the x's and x tildes, but you only get to see them in pairs. So I show you x1 and x1 tilde, but I don't tell you which one's which. So you can look at all their values, you can look at everything together. As long as I don't tell you which one of each pair is which, whatever you do is still going to generate valid knockoffs, and you're going to get exact false discovery rate control at the end. So you can overfit to your heart's content. Of course, if you overfit too much, all you lose is power, because you're just going to do a bad job modeling your data. But you're not going to lose false discovery rate control. All right, so then on the other end of the spectrum, if you really know a lot about your data and you want to incorporate that knowledge, you can take a Bayesian approach. So you can choose a prior and a model, and for instance, Zj could be the posterior probability that Xj actually contributes to the model. And again, even if you're completely wrong about your model, even if your MC-MC doesn't converge, your prior is wrong, your model is wrong, you still get exact false discovery rate control, but to the extent that your prior information is correct, this is really going to improve your power. And we've done simulations where we see you can get big benefits, but again, we're actually theoretically guaranteeing you don't lose false discovery rate control. Okay, step 3 I'm going to go through very fast is just showing an example of what this procedure looks like. So I told you in step 1 how to get knockoffs, in step 2 how to get WJs. Now I'm assuming I have WJs, and they look like this. I'm just putting them on a number line. I'm coloring my negative ones red because I'm about to take absolute values. Remember, the first step was to order these by their absolute value. And what I'm going to do, so I'm going to now go down this list by decreasing absolute value. And remember, I'm keeping track of the number of negatives I've seen over the number of positives. And I'm waiting until that curve last goes below Q. So Q here is 20%. Here's the last time it went below. I'm going to stop there. I'm going to reject all the positives that are to the right of this. So notice I'm not rejecting Q10 because it's negative, so that would be evidence against it being important. So I'm only rejecting the positives. This would be my selected set. And again, this would control the false discovery rate. To give a little intuition for that, so why am I keeping track of this? Who knows? I'm going to tell you. So remember, the false discovery rate is the fraction of null xj selected divided by the total number of xj selected. This is just the definition. This is just the definition applied to my procedure, because this is exactly how I select xj's. So the number of nulls that I select are the positive with absolute value greater than tau hat. But remember, by the coin flipping property, the number of null positives is going to look exactly like the same as the number of null negatives, right? Because the nulls have coin flip signs. So this is roughly equal to the same thing with the negatives on top. And then if I get rid of the word null, all I've done is increase this thing because I've increased the numerator. And so remember that the inside of this is exactly what I'm keeping track of on the y-axis here. So this sort of serves as an FDR hat. And thus it sort of makes sense that we keep track of this FDR hat as we go down the line, and we stop at the last time that the FDR hat is below the thing that we're trying to control our FDR. This is just to give some intuition behind that, step 3. Okay, so now I'm going to really speed. I have numerical results to show that this is a powerful procedure, more powerful than alternatives. Black line is ours, it's most powerful. The black line is ours, it's only second most powerful behind the procedure, which uses those p-values that I showed you the histogram of before, which are nowhere close to valid. So the green line here is using those invalid p-values and hence is not a valid procedure. This is why it's more powerful, so you should ignore the green line. And the black line is the most powerful, black line is most powerful. Black line becomes less powerful when we use a procedure that does not retain control when the variables are actually correlated. And that's what happens if you just use marginal p-values, which ignore all the other variables. That's only going to work if you actually have independent covariance. Very rarely the case in practice. And so that's going to stop working. Our method continues to work. Okay, now I have the data. So what time? I mean, I have 5 minutes before 1:30. Should I stop?
It's up to you.
Okay. And are people actually going to leave at 1:30, or are they going to stick around? Okay. If people are actually going to leave at 1:30, then I'm just going to tell you. That I told you a little about my data. You get the same result if you actually use the exact existing genomic imputation software. So we take the software that they use that biologists use to model genome, and we use that as our distribution for X. And so that's the only assumption we're making is one that actually comes from the domain scientists themselves. And we get more power. This I'm going to skip. This is another robustness plot that we can show that seems to work on that actual data. And then this is my last slide. And that's it. Thanks.
Can you go back to the algorithm that creates X tilde? You built an elegant.
For one of them, yeah.
You built an elegant house that started from the roof and you went all the way down to the foundation, and I missed floor 5.
Okay. Floor 5 coming up. There we
So
go.
algorithm 1,
Yeah.
L is the law, which
It's a
is
law,
a
yeah.
probability distribution.
Just conditional
So it's
probability.
conditional probability distribution of X sub j given a bunch of other stuff. How do you sample from that? If you're not sampling from the argument, you're sampling from the conditions.
Yeah, exactly. Well, so I'll say 2 things. So one is that because I, in theory, know the full joint distribution of X, and I'm the one sampling the xj tildes, so I certainly know their joint distribution as well. In principle, I know this thing, right? So it's not unknown. But computationally, it doesn't mean I can sample from it.
Yeah, it doesn't explain how to sample
It does.
from it.
It absolutely does. So that's the second thing I'll say, which is that's why I said that this is in principle, this is really a proof device, showing that knockoffs works no matter what your distribution for X is.
So you sample in some way such that.
So I'm saying you can sample, right? So in principle, one could sample. This is a distribution, and samples can be drawn from it.
But if you draw from it, you get draws from X sub j.
Yeah.
Okay.
Oh no, sorry. Sorry. This is the law. Yeah. I think maybe I understand better the question you're asking. I'm sampling from the law of xj, which means that it doesn't have
Which
to.
is the probability density of
The
X.
probability density of xj given these things, but conditionally independently of xj. So I'm actually not looking at xj when I sample it, but since I know the distribution of xj, so it doesn't actually depend on the observed values of xj.
Okay.
It only depends on its conditional distribution given these other things.
So you draw from the distribution of xj and you call that X tilde j.
Yep.
So all you're saying is you just replace the observed value with draws from the same distribution. So
The same conditional distribution. So note that this is a particular conditional distribution that actually changes as I go down the line. So it's not the same. It has to have the same marginal distribution, right? That's like saying that this entries in the top corner here and the bottom corner here have to be the same for the different
okay.
things.
So I'm just trying to get the main intuition of the whole procedure.
Yeah.
So you redraw the data from the data, sort of like bootstrapping.
Yeah.
And then why is that helpful?
Because then by redrawing it from a distribution that creates this exchangeability property, right? So that the distribution of the xj's, of the x tildes, mirrors that of x's.
So if you literally did it by bootstrapping, that would be okay.
No, absolutely not. Because that doesn't actually have the property we want. So if we bootstrap, we would have the property that if we swapped all of these with each other, so I took all the x tildes and swapped them with all the x's, we would have the same distribution.
Okay.
But we wouldn't have the property that it's swapping individual ones because
Okay, that's fine. Let me just get the simplest possible case. So let's say we're willing to assume that the data come from a multivariate normal. And we want to get the x tildes from the x's. And so we estimate the means and the variance covariance matrix, and we draw from those an n by p matrix. And those are our x tildes. Okay.
That's not valid.
That's not valid.
No.
Okay. Well,
You have
what's
to,
the
so,
simplest?
Yeah,
give me
that's
the
what I'll tell you, right? So this is multivariate Gaussian. So I have I'm assuming mean 0. So I have a covariance matrix. I'm now going to draw, so I already have my x's, right? And this defines the full joint distribution of all 2p variables. And so knowing this, and knowing my original x's, I now need to sample these x tildes from the conditional distribution of x tilde given x. And of course, since it's multivariate Gaussian, I just need to do a little bit of linear algebra to get that conditional distribution, right? But note that that is not sampling these from sigma independent of the x's, right? It's important. The dependent structure between them is important so that when I swap them individually, I maintain this full joint covariance matrix. And that's what this, there's a lot of things being kept constant. The only thing that's changing is these p things, which are the off-diagonal diagonals. So these would be valid outcomes. And that gives me the coin flipping property, which gives me these IID signs, which I then plug into a procedure that you can sort of imagine. If I know that I have IID signs for my nulls, I can do something good with that, right? It's a nice statistical problem.
Yeah. From the stop rule you described, the Q is actually sort of upper bound of the FDR, not the true FDR.
Correct, yeah.
And you don't know what true FDR is.
Correct.
Okay.
The true FDR is going to depend on the amount of signal in the thing. So, right, for instance, if all of the variables were non-null, my FDR would be exactly 0, right? Because I can't make a false discovery. So, but of course I can't know that, so I can never exactly control the exact value of the FDR.
All right, that's all the time that we have, but I'm sure you could email him or ask him some questions.
Please do.
afterwards.
Thanks for having me, and thanks for all the engagement. Appreciate it.